Good day, folks. Welcome to my YouTube channel. Just do the right thing, like my videos, and download and subscribe. Share with your friends and families. Watch my videos till the end. Thank you for so much for the support that you have given me thus far. We're going to look at a grade 12 topic, the extent of rate of reaction. It's called reaction rate or rate of reaction. Now, what is a reaction rate? In a nutshell, when we talk about the reaction rate, we are talking how fast or how slow for the product to be formed, or how fast or how slow the reactant to decrease while the product increases. So, how fast the reaction takes place in a nutshell. But according to the exam guideline, we say reaction rate is a change in concentration of reactant or product per unit time. So, as I've mentioned, in a reaction, there's a change in concentration of product of reactant. The reactant's concentration decreases, so there's a change in that concentration, while in the reaction the concentration of product increases at a given time, so that per unit time is very important. So it has to do with time, as the product as the reactant decreases and the product increases. Reactants are decreasing in mass, in number of moles, and concentration, and also the products are increasing. That's the rate. Now there are conditions for an effective collision. So the reaction, it has to be in a reaction there has to be a collision, and there has to be an energy in the particles. Now the conditions for an effective collision, there has to be an effective collision in the reaction, right? The particles have to be correctly orientated. So the particles that are colliding, or the particles that are reacting, there has to be correctly orientated. That's not correctly orientated. That's not correctly orientated. There has to be like that. The particles, the orientation, it's how they are facing each other while they're colliding. And another thing, the kinetic energy of the particles, it has to be greater or equal to an activation energy. We know what is an activation energy. It's an energy needed for a particle to for a reaction to take place. So those particles, they have to be have there has to have a sufficient kinetic energy for a reaction to take place. So if it's not sufficient, there'll be no reaction there. So if you're looking here, all these are particles, right? These are particles, but these specifically, these particles that are here, these are the ones that has the sufficient kinetic energy. So these ones are the ones that are making the effective collision. But these ones, the collision that they make is not effective, so they're not making a reaction. Now, very important factors that are affecting the rate of reaction, right? We're going to talk about the concentration, right? So if we talk about the concentration, we're talking about the pressure as well. You need to keep that in mind. So if we're changing the concentration of the reactants, right, changing the concentration of reactant, one of the reactant, that means a higher concentration, higher rate of reaction. So if you're adding more of the reactants, that means that reaction will take place faster, right? Same as you decrease the concentration, the reaction will take slower, right? The surface area. When we talk about the surface area, guys, we're talking about the state of division. If you have a granule of substance, and you change it into a powder, it will take place faster. Like for example, if you're taking a pain tablet, you consume it with water. Let's say take 5 minutes for it to heal whatever pain that you have. But if you take the same pain medicine now, but in a powder form, that tablet, it's in a powder form now, it will take lesser time for it to react. Let's say it will take 3 minutes. So when we talk about the surface area, guys, we're talking about substance that will be in a powder form, or in a granule, or in a powder form. Yeah, like we're changing something from a tablet form, which is a powder form, to a what, to a powder. So a surface area, guys, it's a state of division. yeah, in a solid substance. Now, a temperature, when we talk about that, when you increase the temperature of the reaction, higher temperature, higher rate, faster rate of reaction, right? And the particles will be faster there because the temperature is an average of kinetic energy. Guys, will dwell more on that. Now, catalyst. When we talk about the catalyst, we talking about a substance that a substance that increases the rate of reaction. Right, it increases the rate of reaction without undergoing in any permanent change. Does not take part in the reaction. The catalyst. So the catalyst, its part is to increase the rate of reaction. But I'll tell you the other things that are important about the catalyst. Now, the reaction rate formula, guys, it's very important. Its a rate is equal to change in concentration. This is the original definition. Change in concentration over time. So that's the reaction rate. Um, the change in concentration. Now, guys, the units here are very important. So since it's change in concentration over time, that's its concentration. So the units there, it's going to be mole per dm3 divided by time, which is, let's say time, maybe it's seconds. It's going to be seconds. So when you write that, it will be mole per dm3 per second. Sometimes it can be minutes. You can say per minute. Yeah, it will be per minute. Let's say our rate now it's change in mass. It depends on what substance that we are talking about. Change in mass, it will be gram per minute or gram per second, doesn't matter. Or our rate, it's based on volume, change in volume. So it will be dm3 per second, or per minute, right? That's the rate. That's how you calculate the rate. We know when we say change in concentration, that means we say concentration final minus concentration initial divided by the T final minus T initial. I hope that makes sense, guys. Now let's go to calculating the rate of reaction, guys. In the rate of reaction, in the whether you're calculating using concentration, you're using mass, volume, or number of moles, it depends. But now when you calculate the rate of reaction using the products, let's say in the reaction, they say there's a product of water there. They said calculated the rate in which the water is formed. So in your calculation of rate there, guys, there will be positive sign there. You'll be positive. It will be positive, positive, positive. But if it has to do with the reactants, guys, whatever that you're calculating the rate of, it's in the reactant. In the rate will be what? Negative there, negative there, negative there. Right? It's very important. Reactant, negative. Product, positive. Very important, guys. Now, let's go to the most important part in this topic, explaining the factors in terms of collision theory. Right now, when temperature is increased in a reaction, guys, we know, of course, the rate of reaction is going to increase, as I've mentioned earlier. But now, in terms of explaining according to collision theory, guys, you have to state what is happening there and put the important points there in a bulletin form. You do not write big paragraphs or full page explaining. This is mostly 5 marks at max. Minimum it's 2. So if it's 2 marks, that means 2 points. 3 marks, 3 points. 4 marks, 4 points. 4 points, guys. Not paragraphs, big paragraphs in a bulletin form, right? When temperature is increased, that means the average kinetic energy of particles has increased. Now it says particles have a higher kinetic energy, and more particles have kinetic energy that is greater or equal to an activation energy. It's very important, these points, guys. This point and this point, very important. And more effective collision per unit time take place. Very important that the per unit time there, guys. These points you write as it is. These points, right? You need to mention them. And particles have higher kinetic energy. More particles now here will have a kinetic energy that is greater or equal to. As if you're looking here, and more effective collision per unit time, and therefore the rate of reaction. Guys, when I talk about the more particles, initially if you look at this graph, guys, this is a original graph when the temperature was not increased with the original temperature. Guys, if you look here, these are the particles have the kinetic energy that is greater. Do you see there's the activation energy, which is these ones are the ones that are doing effective collision. Now, when the temperature is increased, if you're looking when the temperature is increased, our graph changes to this. Ne? And but now, if you're looking here, there are more particles now have a kinetic energy. So these particles that are here, they have a kinetic energy that is what greater or equal to the what the activation energy. That means the energy that they have, it's enough for them to take the to for colliding effectively. Guys, these points, they're very important. When they say explain according to collision theory, explain it them like this. Right, now let's go to concentration. Concentration, guys, when we talk about the concentration, it's a number of moles per unit volume. Right, now concentration, guys, if you look here, there are particles, small number of moles per this volume. Now there, when we increase the concentration, guys, that means there are more number of moles per this volume. If I hope you can see that. Now when you increase the concentration, that means you are increasing particles per unit volume. There are more particles per unit volume, or more particles with correct orientation. There are more particles now. This is very important, guys, this point. More particles per unit volume, or you can write that any one of that, or and then you say more effective collision per unit time. Alternatively, for that, you can say higher frequency of effective collision, and therefore the rate of reaction what increases. Very important, guys. So from here to here, the rate of reaction increases. Graphically, guys, this is the original concentration, and now when you increase the concentration there, the graph will be on top of the original one, which is this is the one with the lower concentration, and this one is the higher concentration there. If you're looking there were particles here with the lower concentration, but now if you increase the concentration, there will be more particles now more particles per unit volume. It's very important that, guys. Right, catalyst, guys, very important here. When you explain according to collision theory, you do not say the catalyst speeds up the reaction. You do not mention that here. You say a catalyst provides an alternative pathway of lower activation energy. If you remember the graph of exothermic or endothermic, if you add a catalyst there, there will be a new path. Now the path, the original path there was from reactants to activated complex to product, but now if you add a catalyst, you lower the activation energy. That means you're providing an alternative path with a lower activation energy. Do you see the activation energy was that? But now the activation energy is lower, and you're providing an alternative pathway. Now, a catalyst provides an alternative pathway of lower activation energy. More molecules have sufficient or enough kinetic energy. Guys, if you look in this graph, the Maxwell-Boltzmann bulk distribution curve, the activation energy was this before. This is the initial activation energy. But now if you add catalyst, that means you are lowering. Let's say this was 300. When you add catalyst now, that means you're lowering the activation energy. It's going to be what now? 250. So if you are lowering the activation energy, that means you are decreasing the minimum requirements for the the particles to enter there. So if you look here, there are more particles now since the activation energy has been lowered there, right? More molecules have kinetic energy greater or equal to activation energy, more effective collision per unit of time. Therefore, the rate of reaction will increase there. That's very important when it comes to catalyst, guys. Now let's look at the surface area. When we look at the surface area, guys, if you look here, this is a solid. It's one solid that is together like a tablet. You see, it's a one solid like a tablet, but now if you grind that object into pieces, you break that into pieces, that means you are increasing the surface area. The surface area what increases. Now the surface area here is what is lower. Here it has lower surface area. Here it has a higher surface area. Have higher surface area, that one. So the more you increase the surface area, the higher the rate of reaction. Now it says here in the notes here, when the surface area or the state of division, the other word of the surface area, guys, is the state of division, increases from lump to a powder. We have this lump to a powder. The surface area of compound X of X powder is greater than the surface area of compound X in granules, right? So it's very important. Now, this is how you explain. You say the surface area of compound X is powder is greater than the surface area of compound X in granules. We're comparing same molecules, but in different state of division. Or you can say more particles are exposed, or more particles with correct orientation. That's 1 point, guys. Any of those will give you a mark. And then you say more effective collision per unit time, or you can say that's 1 point, higher frequency of effective collision, and therefore the rate of reaction is high. It will be high. Now, guys, we are done with those, which is the factors that affects the rate of reaction. I hope you can remember them. And then let's look at the methods of measuring the rate of reaction. Now we're going to look at the liberation of gas, the reaction that liberates gas. Now, like this one and this one, do you see there's a gas in the product? There's a gas in the product as a byproduct. Now we're going to look at this method. Method 1, we have a zinc and hydrochloric acid in a reactor to give you that, and there's a hydrogen gas that is produced. Now in this method, guys, we using the conical flask with a stopper there and a pipe that connects to a graduated syringe, the graduated syringe, and then there's a zinc there and the hydrochloric acid there. And now it says close the reaction container with a rubber stopper and collect the gases in a syringe and measure the volume of gas collected in the syringe regularly. So, guys, as this reaction progresses, there will be a gas that is released that will be captured in that syringe, and then we measure that gas there regularly, which means in time intervals. Let's say in every 2 minutes I measure that gas, so I have to have a stopwatch where every 2 minutes I record that gas there, the increase of gas. Guys, there will be a the syringe, it has that something like a piston. I just forgot the name of that. As the gas enters there, it will be pushed back, that piston there, right? So graphically, guys, when we look at the graph of product, if you have seen in the beginning of this video, I was telling you, as the product form, the graph when the product is formed is going to be like this, and when the reactant decreases, it will be like this. So the volume, guys, it will start from T0 times 0. The volume of gas will increase like that. And then, guys, if you look at this curve, we can even determine the rate of reaction there by looking at the curve there. There the reaction is what at T1 is fast, at T2 the reaction is slow, and then at T3 the reaction stops. So the rate of reaction there is fast, and the rate of reaction there is slow, and the rate of reaction is reach completion. So, guys, when you look at the graph there, the slope of the graph is flat, is 0. This one is less steep, that means it's slow, and here is steeper, that means the rate of reaction is fast. The rate of reaction increases there, right? Very important, very important there. Now it says here rate of reaction equal to gradient. So the gradient there at T1 is high, lower and equal to 0 there. So guys, this explanation, it explains this graph there. And then if you have two, now you're repeating the experiments there. You have experiment 1, experiment 2, but you're increasing one of the factors. Let's say you're doing it at a higher temperature or higher concentration, higher surface area, or you're adding a catalyst. So this graph, guys, here you have three graphs now. Let's say you've conducted three experiments, but you've changed one of the factors. This is the original one, but this one is obtained when the temperature has been increased, concentration increased, and state of division has increased, or you added a catalyst there, right? But this one that is below here, that means you have decreased from this original one. You have done it at a lower temperature. Let's say you have done it at a lower temperature, or you decrease the concentration, you decrease the state of division, or you added a catalyst. So guys, here it's a higher rate because this one is steeper, and then this is a low rate, and then this is the lowest rate. Always the one on top there, it is the highest rate, and then low rate and faster rate there. Now guys, let's look at this method now. This method, it's a calcium carbonate with hydrochloric acid. It gives you calcium chloride and water and carbon dioxide. This one as well, you use the carbon dioxide. Now you have the content in this conical flask. It's open there, it's not closed, and you have the calcium carbonate there with an acid. Now as the carbon dioxide is released there, the mass, this is the scale, guys, this is the balance, this is the scale. The mass of this content of this beaker will decrease there as the carbon dioxide is released there. The mass of that decreases. So we're measuring. It says the reaction takes place on an open container on a scale. Measure the mass of the reaction mixture regularly. So we'll take even the stopwatch here and measure the time. Let's say every 2 minutes we measure the mass. We write it down, we record, we measure the mass, we write it down and record. Right? Now it says the mass in the beaker and its content decreases as the gas escapes, as I've mentioned. So the initial, this is the graph of mass versus time. So the initial mass of this container before it decreases, as the reaction starts, it decreases the mass, it decreases the mass, it decreases the mass, right? And then if you look there at the slope, if you look at the tangent there, if you just draw a line, a tangent there, you see the gradient there is steeper. That means the reaction at T1 is what? Is faster. And then the reaction at T2 is what? Is slow. And the reaction at T3, it has what? Stop. It's the same as this one, but this one it's for the volume, the increase of volume of gas. This one is a decrease of mass of the reaction. Now it says a T1 and acid initially is high, and the contact area of solid is still great and high rate, which is there's still a high rate there, right? And then at T2 it says the acid decreases its contact area, and then it decreases the rate of reaction there at T2, and then the reaction stops there, guys. So there will be one mass, there will be constant mass every other 2 minutes. Now the mass will be the same, even same here. The volume that is produced will be constant there. Very important. So in this graph, guys, this graph is fast. If you increase, this is the original one, this one. If you increase now the temperature, your graph will be like that. Now from the original one, let's say if you decrease the temperature, the graph will be like that. So this curve, guys, this is the lowest rate of reaction, and this is the fast rate of reaction, and this is the fastest rate of reaction. Very important, guys. Now guys, the practical skill for this, finding the dependent and independent variable here. Let's say you're investigating between concentration and the rate of reaction. You want to check how does the concentration affect the rate of reaction. The independent, guys, it's what you are changing. You'll be changing the concentration to check the rate of reaction. So the independent, it's what you are changing, and the dependent variable, guys, it will be the rate of reaction. But now if you're doing in the method 1, which is method 1, when I refer to method 1, I refer to this. When I refer to method 2, is this. Method 1 is the one for gas, and the method 2 is the one where you measure according to mass, right? So here, guys, the the dependent variable, it's always the rate of reaction, or you can say the amount of volume per unit time. Very important to say the amount of volume per unit time. And then the control variable, guys, it's always what you did not change. You did not change the temperature, you have changed the concentration, so it will be the temperature or the surface area or the absence of catalyst, right? Let's say you are checking, you finding the investigating between temperature and rate of reaction. So the independent, it's what you are investigating against the rate. So you're changing the temperature, that's the independent, and the dependent, guys, it's the rate of reaction or the volume of gas. If it's method 2, if it's method 1, it's a volume of gas per unit of time, or if it's method 2, the one with the mass, decrease the mass, is going to be the mass of the container per unit of time. Now if you changing the you're investigating between the surface area and the rate of reaction, so the dependent variable will be the surface area, and the independent surface area, and the dependent, it will be the rate of reaction. Catalyst, it will be the independent variable, and then the rate of reaction, it will be the rate of reaction. Guys, the control variable, it's what you did not change. So let's look here. You see, this is the catalyst and the rate of reaction. So you can't have a catalyst here as a control variable, because it was not fixed. The catalyst is what you have changed. So what you did not change is the concentration and the temperature and the state of diffusion. I hope that makes sense, guys. Cheers, bye.